All right, we're going to get started. Thank you all for joining us today, and welcome to our webinar entitled Low Cost, High Value Opportunities to Reduce Embodied Carbon in Buildings. I'm Rebecca Esau, manager for RMI's Carbon Free Buildings program, and I will be your host for today. This is a 60-minute session, and we have 3 speakers who I will introduce in a moment. And they will be discussing a new report by RMI, which outlines opportunities to reduce embodied carbon in buildings at little to no cost premium. So this is all using methods, tools, and materials that are available today. If you have not had the opportunity to see the report, I will drop a link to the download page into the chat. And if you do have questions during the session, please type them into the chat using, or I'm sorry, please type them into the Q&A questions and answers window, which you should see at the bottom of your page beside the chat function. And we will try to actively respond to your questions throughout the presentation. Depending on time, we may also have a few minutes at the top of the hour to have the speakers discuss some questions that come up. So with that, our speakers for today are Matt Youngklaus, who is a researcher in embodied carbon and PhD candidate at the University of Colorado, Boulder. And before focusing on his PhD, Matt was a manager here at RMI and the lead author of the Reducing Embodied Carbon in Buildings report, which we will be discussing today. Then we'll have Steve Clem, who is Senior Vice President and Regional Director of Pre-Construction at Skanska, USA. Steve and his team partnered with RMI to develop the case studies that are part of the report. And through these case studies, we were able to demonstrate an embodied carbon reduction savings potential of 24 to 46% at cost premiums of less than 1%. So Steve will be talking more about this process of developing the case studies as well as the results. And then our last speaker will be Megan Lewis, senior researcher at the Carbon Leadership Forum, where she leads research on procurement of low carbon materials, as well as embodied carbon policy, both in the public as well as the private sectors. And Megan was a key advisor in the development of this report. And today she will be talking about market drivers for low embodied carbon construction, including policy, emerging technologies, and carbon positive materials. So with that, I will pass it off to our first speaker, Matt Youngklaus.
Great. Thank you so much for that, Rebecca. Very excited to be back with some of my colleagues from RMI and Megan and Steve as well to present this report. And I wanted to start off with the basics. So next slide. I want to start with what is embodied carbon. Next slide. So we start the report off at a pretty high level, and we want to make sure that everyone who's attending here today kind of has the same basis of understanding of what this report focuses on. So embodied carbon overall refers to the greenhouse gas emissions associated with the manufacturing, transportation, installation, maintenance, and disposal of building materials. And again, embodied carbon can refer to more than just materials in the built environment, but here that is what we are focusing on. And those upfront embodied carbon emissions really focus on any embodied carbon emissions that are released before the building is constructed. So a real focus on the manufacture and extraction of those materials. Next. And so, just putting it a bit more graphically, we can see, again, upfront refers to the extraction, manufacturing, and even the construction on site. And then operational carbon is something that we're very familiar with in terms of energy efficiency, and a lot of the areas that RMI has historically focused on has a lot more to do with the way that energy is consumed in the building. And then beyond that, end of life carbon deals with operations and maintenance, repair, demolition, disposal, and potential recycling of the materials. So next, I'll touch on why embodied carbon is important to us all. So our buildings have a hidden climate impact, and it doesn't just have to do with global energy consumption, which has been the focus of RMI and many other groups over the years. And so 28% of global energy related emissions are spent powering our buildings, but 11%, and by some estimates, that's actually a conservative number, but 11% of global energy related emissions have more to do with the embodied carbon related to our buildings. Beyond this, embodied carbon is very significant, and it becomes more and more significant as our buildings become more efficient and our grid becomes cleaner. The chart on the left here kind of shows what we might see as a business as usual type building with a certain chunk of the emissions pie devoted to operational carbon, so the carbon emissions associated with consuming energy in the building, and another chunk associated with embodied carbon. But as we make our buildings more efficient and the grid cleaner, that chunk associated with operational carbon gets smaller, and actually embodied carbon can get larger, even if it doesn't remain the same as it is shown here. More efficient buildings can have a higher embodied carbon content if we don't look at decarbonizing in a holistic manner. Next. Similarly, we're kind of showing that breakdown of global energy related CO2 emissions, and building materials and construction currently have the fourth largest source of any energy related emissions at about 11% of the global annual total based on 2019 numbers. Next slide. And again, putting some of these words in a different context, because embodied carbon has a lot to do with what happens up front, what happens before and during construction. Unlike looking at operational carbon emissions, embodied carbon emissions all hit with kind of a pulse of emissions up front. And that's really a big deal because we have a lot of 2030 and 2050 climate goals. And while improvements in operational energy consumption in our buildings are important, as you can see, they're represented by these blue bars. That is a much smaller piece of the total pie, especially if we're only talking about a 10 or 15-year time frame. While over time, operational carbon does become much more significant. So looking at these upcoming climate goals and the fact that we're building buildings at an unprecedented rate, not just in the US, but certainly globally, embodied carbon is a really substantial issue, regardless of the improvements we're making in operational. And next slide, I think Architecture 2030 says a lot of things well on this topic, and they really do a nice job of kind of summarizing the point that I was just making, that as we make improvements in efficiency and renewables, that pulse of embodied carbon emissions are locked in place as soon as a building is built. So again, you can improve the energy efficiency of your building over time. The best time to improve it is up front. We're not in any way saying that those emissions matter any less, but we're saying that embodied carbon is something that is urgent and hasn't gone addressed for a long time. So we really need to focus on it to hit our short-term climate goals. So the next thing that I'd like to do is talk about where we get started. We're going to have Steve and Megan later on talk about some of the specific strategies, but I'd again like to kind of set the stage and provide some general strategies and some general hotspots we see in buildings. So next, I'd like to talk about some of the typical embodied carbon hotspots in buildings in two different contexts. Right here, we really just show some of the key components of buildings attributable to significant embodied carbon consumption or embodied carbon emissions up front. One of the major focuses in this industry is on structural materials. And as you could imagine, the impact of structural materials varies a lot depending on what kind of a building we're talking about. So if we're talking about a single family residential home with wood framing, we're going to see a very different picture for structural materials than if we're looking at a 15-story commercial building with steel reinforced concrete. The embodied carbon intensities and the amount of materials needed for those two different buildings are really significantly different. So you'll see that we can't say structural materials are always X% of a building's embodied carbon. But beyond structural materials, building envelope, so your insulation and air sealing are also quite significant, as well as certain finish materials. So, I think that Megan will talk later a bit more about different insulation materials, but it makes a big difference if we're talking about using something like a cellulose or straw bale for insulation rather than a foam, which is often made out of petroleum products and has different elements that lead to greater embodied carbon emissions. And then looking at finish materials, sometimes it has to do with their embodied carbon intensity per kind of unit, but sometimes it just has to do with the fact that there are certain materials we use a lot of. If you think about drywall or gypsum board, or if you think about carpeting materials, we just use enough of those in a building that a small difference in embodied carbon can go a long way. Next slide. Another way of thinking about this is in terms of the types of materials themselves. And so by looking at this, I'm not saying that these are always the highest specific materials in terms of embodied carbon in a building, but they're some of the ones that we detail in the report and think that it's worth discussing because certainly these materials have different intensities. Similarly to the comment I just made about carpet tiles and drywall, we want to think for these materials, what is typically used the most and in what quantities? Because cement and concrete contribute more to global emissions than steel, but the embodied carbon intensity per unit of weight is actually lower for cement and concrete. The fact is that we need to use a lot of it to build a building. So there are many different ways to think about these. Just to throw a few statistics out, so structural steel is about 46% of the market share for structural framing in basically buildings that aren't single family residential, while concrete takes, concrete or steel reinforced concrete take about 34% of that market share for structural framing, and wood is about 10%. Also, we say cement and concrete here because many people mistake one for the other. One way you can think about it is that if we're baking a cake, cement in some ways is like the flour. It's an ingredient in concrete, which we can think of as the cake, as the whole. And concrete is the second most consumed product in the world, second only to water. One way you can think about it is that there are about 3 metric tons of concrete used per person each year. We could go on with some of these significant statistics, but I think that the key takeaway to thinking about these different materials is really that these first 3, are significant structural materials, and they, can and should be considered not only in how some of these can substitute for others. Typically, timber is a lower embodied carbon substitute for cement and concrete or steel. In some cases, it can be seen as a not only a lower embodied carbon material, but a net carbon sequestering material if it is built in a durable building made to last. But more than anything, we just, for these three materials, need to think of what the best material is for a given circumstance. How can we source a material that is sustainably sourced and sourced with lower embodied carbon, lower carbon emissions in the manufacturing and extraction process? And what materials can we use to make a building last its longest, given some of these other elements? Because a building that lasts long is going to basically store that embodied carbon for a longer period of time, and typically give you a better bang for your buck on the upfront embodied carbon. Next slide. So the report lays out opportunities for reducing embodied carbon in a few different ways. And so if we jump through the next 3 slides quickly, we can see that in early design, we're looking at whole building design concepts for reducing embodied carbon. As you move farther in the design, material substitution is one category of strategies that we can look at. And then next, specification is kind of the way that we can tweak embodied carbon at the later stages of a more developed design. And so within whole building design concepts, what we're really talking about here are making broad decisions that can reduce embodied carbon. So, for example, we could talk about using an existing building, which can really substantially decrease the amount of embodied carbon for a project because we're using materials that are already in place, or using fewer structural materials, or focusing on structural materials with much lower embodied carbon, as we referenced on the last slide, like timber products. So next, for material substitution, what we're really talking about is using alternate low carbon materials that do the same job. And so timber instead of steel is actually kind of a tricky example to give here. But I like the second example we have here of using carbon sequestering materials. For example, a carpet tile or a wall finish material. There could be one that is net sequestering that serves the same function. The reason I say timber and steel gets tricky and might not actually go under this category is just that you need different amounts of each of these materials to serve the exact same purpose. But as you can see, moving left to right, we're going from completely rethinking a building design. Then when you're farther along, maybe you can just switch one material for the other. And then next, with specification, we're talking about specifying a carbon limit for a material. So it could be specifying an amount of supplementary cementitious materials or other makeups for a concrete that would allow it to have a lower embodied carbon content. So moving left to right, we kind of go more holistic to more specific. The point is that there are strategies that make sense for each point in the building design process. So even if you're working on a project now that's fairly far along, fairly advanced, there are still strategies that you can take on. And so next we'll talk about this in a bit more detail. And I'll say that the points we're going to show here are put in a much larger graphic with more detail in the report. So I'd love to send you over there. But if we quickly go through the next 3 slides, we can show that whole building design and then material substitution and then specification and procurement kind of overlay nicely with these 6 steps in the typical design and development process. So starting with pre-design and site selection, some examples of actions we could take to reduce embodied carbon might be considering building or even just material reuse from the original site, assessing the site for an optimal low embodied carbon foundation, or setting a budget for embodied carbon. In conceptual and schematic design, we might think about design for more efficient material use, thinking about longer term use for the building, again, to get the most out of the materials that we've spent up front. A more durable, long-lasting building typically has lower embodied carbon. Designing for disassembly and reuse, or conducting a whole building LCA. I won't touch on every single one of these in the next few categories, But in design development, we might think about specifying those low embodied carbon materials or substituting materials. In bidding and procurement, we might think about including some of the goals that we've already set in procurement language, or requesting the right information from those who are bidding on our work. In construction, we can think mostly at this point, design should be more or less complete. Some decisions might need to be made, but we want to focus more on waste reduction and accountability for our contractors delivering on embodied carbon goals, not substituting out the materials that we carefully chose for things that might be higher embodied carbon. And at the end, in occupancy, it's really about applying lessons learned and moving forward to the next projects. So in the next slide, I'll just show you a quick example of the graphic that we have in the report. Without digging into this, I'll just say that in addition to identifying some of the strategies on the last slide, we also talk about what primary stakeholders are involved in making each of these decisions, whether they're the decision maker or just need to be involved. So on the next slide, I'll also just note that the report digs more deeply into tools. I know this is something that Carbon Leadership Forum has done a lot of work on, publicizing the right tools for the right job. We talk about specific strategies like redevelopment and reuse of existing buildings, which, I wish we had time to go into deeply here, but just considering reuse can decrease the embodied carbon footprint of a project by 50 to 75%. We often don't do it because it's hard and sometimes expensive. And then there are just more examples of strategies throughout the report. And so next, we'll dive into the case studies on the economics of low embodied carbon buildings. So I'll hand it over to Steve.
Yes, thanks, Matt. Can everybody hear me okay? Excellent. All right. Well, first of all, thank you very much for attending. I appreciate this opportunity to partner with RMI, and Skanska has been working in the space for a long time. I'm in that legend that you just showed, Matt, the yellow icon, the builder contractor, that's us. And we are really pleased to be able to share some of our learnings over the last few years and some real life projects that went into the report. So let's go ahead and go to the next slide. So we're going to look at some case studies. I think that the thing that's important to just know here is that often these studies, these sort of academic studies, are done using a prototypical project or some type of rectangular box that fits into a energy modeling system easily and has a certain number of floors and a certain solar orientation and some ribbon windows and a bunch of things that are gross generalizations. And in this case, we identified 3 real projects that have been constructed or in progress of construction. And as a result, we were able to look at actual quantities and actual materiality of those projects. And so that varies or that differs from a number of studies like this that we've been involved in the past, and I think hopefully lends additional credibility to the results. So if we go to the next slide. So we looked at 3 different construction types, and those are you saw the types of carbon intensive areas in the building. So obviously we aligned with that. We have a steel reinforced concrete slab, and we have a wood framing with the concrete slab. So that's a building that has a use separation at the first floor, and then we have a tilt-up concrete. That's a fairly common construction type in warehouses, fulfillment centers, even data centers. That it's great for large format buildings. It's inexpensive and very quick to build. And so what we did, excuse me, what we did was we looked at business as usual. And these were projects that didn't really have anything, outstanding, goals or even or anything that was actually would make them too terribly unique so that they would skew the results at all. These are fairly standard projects, and that business as usual would be code required, municipality specific, those types of things. So the baseline wasn't that these are super high ambitious achieving projects. This is intended to be sort of state of the shelf market projects. And then the second look at it was a very cost effective low embodied carbon version, and primarily through a analysis of the EC3, the embodied carbon and construction calculator tool. And that is how we approach these. So if we go to the next slide. So in addition to their use, this is just a little bit more of a highlight, but we saw that multifamily office and these warehouse buildings, the attempt was not to shy away from any type of building in particular, but to focus on ones that could potentially be able to move the needle in terms of volume. So the types of projects that are the most of which are being built, and the ones that have the greatest potential. So if we can go to the next slide. So here's the spoiler. If you wanted to read the report, and you were, I should have told you to close your eyes, but I think we heard it at the get-go. Some pretty remarkable results, and then we'll talk to you how we got to those. So in the steel reinforced building, we were able to project a realized savings of 46% over the baseline business as usual case, and 41% for the wood frame, and then bringing up the rear at 24% was still a pretty remarkable reduction. Is 24% of the tilt-up concrete. So let's go to the next slide. And the next one, please. So this building was a concrete building with conventional mild steel reinforcing as well as post-tension, 200,000 square feet on 5 floors, mixed use. And so, we projected some of the interior build out as well, and all above grade. You can see here in this breakdown that the baseline or business as usual is the 100%, and probably not surprising that the majority of the savings were found in concrete and alternate mixed designs and approaches for concrete. The steel and the rebar also played a large role just because of its prevalence in the design. And then the glazing and aluminum package was also a small component of that. So those add up to this 46% reduction. You can see the absolute number there at the bottom in red, or actually in white in the red box. And what we did is we looked at the costs of similar concrete mix designs or revisions to sourcing on rebar, glazing, and price those up for the real quantities. And that resulted in, for this particular project type, a total project cost increase of just under 0.5% of the total project cost. So, I like to say that these are, as a builder, our cost margins are very low. So I'm very cautious about saying anything is negligible, because our typical gross margin is 3%. So this represents a pretty good fraction of that. But I do like to compare this to things that we take for granted on project costs, such as insurance and other things that are meant to protect the project, and rightfully so. But we can look at these types of investments as protection against a bigger sort of existential threat. So just to give you an order of magnitude of those numbers. So the next one, if we can move to that, this is the mid-rise stick built. So you can see sort of a representative image there of the wood frame, 125,000 square foot, multifamily residential. And so obviously the key differentiation there is that it's slightly smaller building, but it is primarily wood, not heavy timber, but primarily nominal lumber, and there is concrete that separates that ground floor use from the upper uses. So you can see there, interestingly enough, that the same sort of methodology here, but the insulation is a big factor here in this building. There is still concrete and some rebar associated with that concrete, but you can see that the way it's distributed is quite different than the other project, and that results in a 41% reduction. So in the same sort of general ballpark as the other project, but just getting there in a different way. And you can see that the total reduced tonnage is 2/3 of the other project. And again, similar price point due to some revisions in the cost of the concrete and the insulation. But the overall the overall price point of this project is less than the other one, and so there are some offsetting things in the numerator and denominator that end up making it the similar overall price point. So the last case study is tilt-up construction. You can see a picture there of one underway. The actual real life project was 360,000 square feet, which is fairly average for these types of buildings. We have, these buildings range from 50,000 square feet to well over 1 million square feet. And so lots of opportunity here. And primary use is warehouse, but it's the exact same construction with some minor revisions that make up most of the Amazon style distribution centers and other things. So you can see there that this building is much simpler than all the rest of the buildings. It's a single floor, and it has minimal finishes and minimal sort of architectural features, and you can see there that the majority of the reduction is right there in the concrete, and the strategies around that continue to be mixed designs, different types of cement. We got that clarification between cement and concrete, which was well stated by Matt, and then replacement for the cementitious materials in those mixed designs. So the next and again, because of this reduction and the fact that the structural system makes up a higher percentage of the overall project cost, the premium is slightly higher, but still coming in at less than 1% of the total project cost. So if we can go to the next slide. So in summary, this is a graphic straight out of the report. I really like how this was presented here. You've got concrete, rebar, insulation, glazing, and finished materials. And so you can see in, almost in left to right in a reduction spectrum where you can make these investments mainly in time and energy. The continuum of the project, the 6 steps that Matt showed, for us, it's primarily in taking those specifications and making sure that we can buy what we think we're getting, if that makes any sense. So a lot of these things are commodities, rebar, insulation. You can get insulation from a lot of different manufacturers. You can get concrete from several different batch plants. Our challenge is to take those say GWP numbers and actually buy that mix and not another one that meets the same strength criteria, is the same workability and durability, but add this critical component of embodied carbon into the selection process. And so that's how we would recognize these carbon reductions, and then the very small premiums associated with doing that effort are listed here. And we expect that premium will go down with time, and we'll talk a little bit about that in just a couple slides here. So next one, just a little bit more in depth about how we approach this. If we just go to the next one. This is really, the fact that it's called embodied carbon and construction calculator. The word calculator is because it basically does, I've got this really simple formula here. We take the material quantities. So we have a database where we do all of our estimates in. We export all of the quantities. We assign them to the associated EPD with that material, and that has an embodied carbon number per unit. And so from there, it's a simple multiplication where and then we end up with this Sankey diagram here. And this is sort of the money shot of the system here, where you've got this wonderful spectrum of colors. But what it's doing here is the first column are the materials. So you've got the structural steel, concrete. Then the second one is the element type. So you can see their columns, floors, so where it's found in the building. And then the last one is really kind of the major building components, the shell and the substructure. And then the last one is the blue bar is, and I'll show you another one here shortly, is the optimal savings for the project. So go to the next slide. This is a little bit more clear to see. So from case study number 1, less of a generic slide, but an actual one. So you can see here that the numbers that have the little upside down carrots, or sorry, the boxes with the little upside down carrots or V's, they show the reductions. So in that, where the cursor just was, the ready mix there, it went down more than 50%, and that's based on a real mix design from a real supplier, a real batch plant. And so all those things add up to, as you look left to right, they're cumulative, and they look at that total, where the conservative embodied carbon estimate pushes it down to that 46%. And so you can see there how those different items contribute. Similarly, in the next one, you can see here the insulation playing the much larger role, and concrete taking second fiddle to that, and then the third is a little more similar to the other one, but where because the substructure or the shell and it's all kind of one thing. That's why those boxes are so cost effective. All of it sort of sits there in that substructure and shell, but a very sort of elegant and informative way to display the information and to then know where to go dive down and look for other opportunities. So if we go to the next slide, again, I use the word academic, and I use that word with all due appreciation of that, and and even some of the sort of real live projects that we've displayed here are all sort of still somewhat speculative on conducting the procurement in a way that realizes these savings. But what I wanted to do, in sort of to counter that that argument, should it arise, is that we're already seeing a real life reduction in GWP intensity of mixed design. So last year, on a major project in the Seattle area, we began to procure work using the alternate procurement method, using like a good, better, best for concrete mixes, and they had to meet GWP targets. And it was amazing to watch that as the average GWP mix design in the region dropped by 18% over the original baseline just in about 9 months. And this was purely peer pressure. It was asking the question. It was materials suppliers getting more savvy about what they need to meet the demands of their customers. It's also about them pushing the question farther up the food chain. And speaking of the food chain, for us, that's the supply chain. And we have a strategic supply chain team. And the major offending component in the concrete is the cement. There's mass consolidation going on in the cement industry in the world, but there are a few major suppliers. And so if you go to their website, like Wholesome, Lafarge, Heidelberg, all these folks, the number one thing you land on is zero carbon concrete. But we need to help them get it out to the individual markets by asking for it in those markets, and they're operating on a squeaky wheel methodology. So the more we ask for it, the more it gets out to those local ready mix suppliers, and we can actually see these impacts on the projects. Next slide. So that's it for me. I'll pass it on to Megan, and I look forward to hearing from her. Thank you.
Thanks, Steve. My name is Megan Lewis, and I'm a senior researcher at the University of Washington at the Carbon Leadership Forum, where I lead our embodied carbon policy research. Next slide. Oh, next one. So I'm going to cover 3 topics today, and I'll try to do so quickly so we can have a few minutes for questions maybe. And all these related to opportunities for deeper reductions for embodied carbon savings. So first I'll cover policy. Next slide. Policy is an essential step to creating the widespread action and transformation needed to rapidly reduce embodied carbon in construction. Broadly, there are two types of performance-based policies for reducing embodied carbon. You can see on the left here, the building approach, which uses a methodology called whole building lifecycle assessment to verify performance. And second, a material approach on the right that uses product LCAs in the form of a EPD to measure and verify performance. These are complementary policy strategies, and depending on the type of policy and the goal, it depends on which one is more helpful to use. So far in the US, we've seen more of the material approach on the right, whereas in Europe, Canada, and Australasia, where policies are also developing, there's been more focus on the building approach. One key thing to highlight here is that the building approach really focuses on designers and the early stages in the design process that Matt highlighted, and captures strategies like building and material reuse, carbon storing materials, efficient structural design, really design related strategies. And then the material approach focuses more on what manufacturers and contractors can do to reduce carbon through procurement and through strategies like concrete mix design, plant efficiency or fuel choices, and sustainable ingredient sourcing. Next slide. Performance-based policies use targets or limits to regulate or incentivize reductions in embodied carbon. So this is typically done through either a percentage reduction target from a baseline or setting carbon intensity limits using global warming potential as measured in whole building LCA and EPDs, as I mentioned on the last slide, that set a carbon intensity threshold that a building or material needs to be below. So as you can see on this slide, we've already seen examples of this approach at both the building and material scale, including credits from the LEED v4 rating system at the building and material scale, as well as carbon intensity limits set by ILFI's zero carbon certification, and by procurement policies like Bike Lane California and Bike Lane Colorado. And the next slide. As described by Matt earlier, the opportunities for reducing embodied carbon vary across the span of the design and construction of our project. Similarly, the best policy lever to drive those strategies varies. So here are some examples of approaches that we're seeing globally to reduce embodied carbon and sort of where they line up in relation to those types of strategies. So from reuse and deconstruction policies to city zoning, land use and building regulations, to building codes, climate action plans, and green building incentive programs, which really can act sort of across the spectrum of solutions, and then procurement policies like Buy Clean that are more about the specification and procurement stage of a building design and construction. Next slide. So here you can see where some of the policy action I described is beginning to happen, from procurement policy at the federal and state level to a variety of policies at the local level. I'm not going to list these off, but I'll just encourage you that if you'd like to find out more about these, to reference the CLF policy toolkit that's referenced here, which includes a periodically updated map of embodied carbon policies in the US, and we soon hope to expand globally. Next slide. And again, here, I'm just briefly including this to give you a sense of the rapid growth of procurement policies in the US at the state and federal level, which is what is covered here, although there's also local procurement policies like in Portland. This year, Colorado and New York just passed new policies, joining California and setting requirements for EPDs and phasing in carbon intensity requirements for the materials specified in the policy on state projects. While not all states that proposed bills this year has passed, so some of the ones on the farther to the right, these states are likely to continue proposing this type of legislation in the future. You can also see here some variations in the scope of these policies in terms of what materials are included, whether they're building or transportation focused or both, and then whether they require only disclosure or also set carbon intensity limits or provide incentives. Next slide. Now I'm going to completely change gears and talk about alternative materials or emerging materials. While policies are driving widespread adoption of existing strategies, such as those described in both Matt and Steve's presentation, this is sort of switching gears to think more about the future and what emerging materials and technologies could unlock greater opportunities to reduce embodied carbon. Next slide. So this slide summarizes here, so in the sort of blue and gray here, summarizes the status of developing alternatives to traditional construction materials and processes, and is taken from the RMI report. So I highly recommend you check that out. These are categorized by their market readiness, from market ready to near market to still very much in development. And I've just bolded a few so that I can talk about the kind of range of strategies or the range of new materials and technologies. So there's plant-based products, which I'm going to talk a lot more about in a moment. Lightweight products, where manufacturers have engineered solutions to provide products with the same performance but less materials. So anytime you're using less material, per unit or per square foot of building, that's going to result in embodied carbon savings. There's CO2 injected or sequestered products that can store captured carbon. And last, but certainly not least, in development is the use of alternative fuels, which is particularly important for high heat processes that are required for certain types of steel manufacturing and cement production. So right now, those are not able to use electricity in production for most of or not all types of steel, but and some types of steel, and then all cement requires just too high of heat to use electricity currently. And so in addition to carbon capture and storage, the use of alternative fuels is a necessary strategy to be able to continue to drive reductions and provide clean manufacturing solutions. Next slide. So this slide, I'm just going to quickly discuss biogenic carbon to explain why plant-based products are an exciting solution for reducing embodied carbon. So you can see here the biogenic carbon flows, which are in blue, and the fossil carbon flows in gray. So primary difference here is, of course, that there are no gray arrows going down. So, fossil carbon, there is no carbon drawdown or uptake over the life. There's only releasing of carbon into the atmosphere when we burn fossil fuels. Biogenic carbon, on the other hand, represented in blue here, you can see this large blue arrow on the left that represents the carbon drawdown that occurs during photosynthesis. Then throughout the processing and manufacturing of plant-based products, as you can see here, so this example is talking about timber products, but you could also think about this for other plant-based products. Some of this carbon is released, such as during logging and manufacturing, but a significant amount of that is still stored in the product. And then when a building reaches the end of its life and decomposes in a landfill or is incinerated, the carbon it has been storing is released, which you can see here at the end. This period while the product is being used and storing that carbon that it drew down through photosynthesis at the beginning of its life when it was growing is why we call these carbon storing materials. So they hold carbon during their life and then eventually release it. This carbon storage is a critical strategy to reaching our climate goals, as it results in the drawdown of carbon in the critical 10 to 30 year period where we really need the most radical reductions in order to stay below catastrophic levels of global warming. So go to the next slide. You can start to see in this table, which is taken from the RMI report, examples of what carbon storage potential looks like when you look at individual materials. And so typically the way this is shown is sort of the green here, which is sort of negative. And again, that just means that until the product decomposes at the end of its life and is no longer being used, it is storing that carbon that you're seeing here in green. And as you can see from this range of products, so there are lots of types of building components that are now available as carbon storing or biogenic materials, from structural materials like mass timber and laminated bamboo is an emerging material, foundations like hempcrete, insulation has a range of product types, as well as cladding and finishes. So if you go to the next slide. This is focusing in on just one type or one category in terms of insulation, where there is already a number of carbon storing alternatives available, like straw bale, cork, hempcrete, cellulose, and wool. Some of these we've already had available for long periods of time. Cellulose insulation has been available for a long time, whereas straw bale is one of the oldest types of insulations that we have. But typically these are not being used in a sort of everyday business as usual project, especially when we think about the commercial scale. And so right now, these are often in the sort of piloting phase, which is really critical for the building industry to grow the capacity to understand how to detail buildings appropriately with these materials, understand their performance requirements, and understand what a pilot project looks like for different building types and climates. But you can also see here that there's a huge range in what that can look like, from it just in terms of the strategies on top, which are, or the material types on top, which are what we might think of as more typical materials, to the carbon storing materials on the bottom. And one of the big things for insulation is obviously the blowing agent that's used in insulation. And so as we make our way towards emerging materials and technologies that can store carbon, there's also just lower carbon alternatives. And so it shouldn't be an all or nothing strategy. If you're working on a project, you can also just look for the lowest carbon material available that works, that your team is comfortable using at this point. And we hope to see pilot projects and growing education and industry make these more available for a broader range of building types. Next slide. I'm just going to quickly share sort of highlights summarizing what some of these next steps are that are expected in both policy and alternative materials. Next slide. So on the left, to continue scaling development and availability of alternative materials requires standardization and agreement on biogenic carbon accounting, increased practitioner capacity to adapt to emerging technologies and materials, as I was just discussing, incentives for manufacturers to help scale from R&D. So things like alternative fuel use require significant upgrades in manufacturing facilities and will require financial incentives, either likely from the government at the federal scale, which is something that's being discussed now, and as well as development of policies that incentivize carbon storing materials rather than only on clean manufacturing for concrete and steel, for example, where we see the most policy action currently. And then in terms of policy, we expect to see procurement policy continue to grow, particularly for concrete. And we expect to see a growth of building scale policies, which I discussed at the beginning of the presentation, that will enable policymakers to incentivize or regulate reuse, carbon storage, and other strategies that occur before procurement. And with that, I will pass it back to RMI to open it up for questions.
All right. Thank you, Megan, Steve, and Matt. And sorry, Megan, there for slight scrolling mishap. Let me unshare my screen here. Not sure how to do that. All right. Can you guys still see my screen, or have I not shared it?
You can see it.
You can still see my screen.
Yep.
Okay, there we go. Okay, great. So we do actually only have about 2 minutes left for questions, and thank you to the speakers who have sort of been fielding these questions as they come on. I might just start off with a really quick question from Kristen about conducting a whole building life cycle assessment. Are you able to clarify how those baselines are established when you are doing a whole building life cycle assessment, where the baseline comes from? Megan, go ahead.
I'm assuming that one is for Steve, or are we talking about the policies that I was discussing?
It refers specifically to policy, so I think Megan.
Okay. So currently the approach that's used by LEED is one that I think is part of the reason that we haven't seen this scale more in the US, which is on developing a sort of reference building that is your baseline, that enables you to have the exact same performance requirements and square footage. But currently developing, which is I think why we're seeing this as a sort of what's next rather than what's already available in the US, is the development of the building carbon intensity limits, similar to the way that we have building energy use intensity limits. So that would require development of either reference models or use of, which is what's done sort of for like DOE is able to establish the energy use intensity for different building types. And either that approach could be used or the collection of large amounts of whole building LCAs, which is more of what we're seeing, for example, in Vancouver, which has a building scale policy. And so they've required disclosure of whole building LCAs over a number of years. And then we'll use that data to set Vancouver specific limits. So I think both of those are valid ways to establish benchmarks. And I think both will emerge in the next few years in the US.
Awesome. Well, thanks so much. I know that we are at time now. So I would just want to thank our speakers again, and for all of you who attended this great webinar. I have dropped in the link to download the report so that you can explore it in your own time. And we will be sending out a recording of this webinar in the next couple days, I think. All right, everyone. Thank you again. Thank you, Matt, Megan, and Steve especially. Take care, everyone.
Thanks.